Good evening, everyone. So, welcome to the live session for week 4. This in this course of hydraulic engineering in NPTEL. So, today's session is mainly based on the concept of boundary layer theory. So, you must have gone through the lecture videos. So, it is boundary layer theory. So, just like previous classes, initially we will discuss the basic concepts once again, which is a sort of recapitulation or revision of the concepts that you have already learned while watching the videos, the lecture videos, and then we will follow, then we will practice some problems which will further clear your concepts. So, first of all, we'll see what is basically a boundary layer, what is its basic idea, and then we'll move to some advanced properties or characteristics of boundary layers. We will try to appreciate both the mathematical nature of the equations that govern this boundary layer flow and which equations or which expressions you need to remember for your competitive exams or maybe your university exams, and then we'll practice some problems. So to begin with, what is a boundary layer? What is a boundary layer? The first question that you should be able to answer is, what is a boundary layer? So boundary layer, just writing the definition. What is a boundary layer? So we can define a boundary layer as the thin layer. Okay, it is a thin layer. It is a thin layer which is close to a wall or a solid boundary. So what is a boundary layer? A boundary layer of a flowing fluid is a thin layer which is close to a wall or maybe a solid boundary. So you can either call it a wall or a solid boundary. So pictorial depiction may be something like this. Say there is a flat wall. Okay. So a very thin layer just adjacent to this wall is known as a boundary layer. But that is just a very basic definition of boundary layer. What is important is what are the flow features, associated flow features inside the boundary layer. Okay. So that you should be able to tell immediately, because this concept of boundary layer is very important from practical applications of fluid mechanics point of view. For example, you are designing a aircraft, the hydrodynamic or the aerodynamic parameters, you will definitely require the concept of boundary layer. In case of river engineering or maybe coastal hydrodynamics, whenever we study the movement of sediment transport or whatever is happening at the seabed or the river bed, there also the concept of boundary layer is equally important. Then in studying the phenomenon of uh, flow separation associated with the flow past block bodies, again there, if you want to understand or if you want to appreciate the flow physics, it is very important to know the concept of a boundary layer. Okay. So first of all, what is a boundary layer? The boundary layer is a thin layer of fluid close to a of a flowing fluid close to a wall or a solid boundary. Okay. Now the important properties of this boundary layer include property number one, or the flow features that you need to remember. Number one is viscous stresses. Okay, viscous stresses are dominant inside this layer. So as we have seen in the last class, say in case of in the last week's lecture live session, we have seen the concept of Reynolds number, which is the ratio of inertial force by viscous force. Now what is the importance of this Reynolds number? If the Reynolds number is very high, we say that the inertial forces are much higher in comparison to the viscous forces, and for high Reynolds number we say that the flow is turbulent. Okay, now even in case of turbulent flow, we get a very thin layer close to a solid wall, which is known as a boundary layer. And though in overall turbulent flow the inertial forces are dominant over viscous stresses, but inside this boundary layer viscous forces are dominant. Okay, so that's why it is very important to consider this. Near to a closed wall you need to consider this thin layer, okay, which is the boundary layer. So this is the first important property, that is viscous stresses are dominant inside this layer. What is the second property? The second property is the main flow velocity. Okay, the main flow velocity, the main flow velocity, the main flow velocity within, sorry, flow velocity within this layer, the main flow velocity within this layer tends to zero while approaching the wall. So what does this line basically signify? This line signifies that, see, these point number 1, point number 2, all these points are related. How? So point number 2, if you look carefully, what does it tells us? It tells us that the main flow velocity within this layer tends to 0 while approaching the wall. Okay, so this main flow velocity tends to 0 while approaching the wall. What does it mean? It means that near to this wall, now as you move closer to the wall, the velocity tends to 0, the main flow velocity. Okay, so this signifies the presence of a velocity gradient. I am writing del u by del n maybe. Okay, so n is a direction, so del u by del n, so it signifies the existence of a velocity gradient. Now if velocity gradient is there, then if you apply Newton's law of viscosity, say for a Newtonian fluid, mu du by dy or du by d1, so this velocity, if this velocity gradient exists, then we said it, because ideal fluid, again, all practically if you look at it, no fluid is perfectly ideal, so there will be some viscosity of that fluid, however small that the value. So whenever there is a velocity gradient, we say that there is shear stress. So that's why the first point tells us that the viscous or the shear stresses are dominant inside this layer, and the second point tells us that there is a velocity gradient. Okay, and these 2 points are, that's why, related to each other. And then what is the third important property? The third important property is uh, the third important property is that, uh, say this is the, let us consider the flow over a flat plate, and say a boundary layer has formed. Okay, say this is our x direction, this is our y direction, and this is our main flow direction. Say the main flow direction, the velocity in the main flow direction, we are symbolizing using this symbol small u. Then the gradient of the velocity, in the normal direction to the surface, so the direction normal to the surface is y, so del u by del y. Okay, the gradient of the velocity along a direction normal to the surface is large in comparison to the gradient of the velocity, okay, gradient of this component in the streamwise direction. So the streamwise direction in this case is x direction, so del u by del x. So these are the three important properties which you should always keep in mind whenever the term boundary layer comes into picture. So the first important point, very important point, is this: within this layer, even if the flow is fully turbulent, within this layer viscous stresses are dominant. Okay, second point is that the velocity approaches zero when the velocity tends to zero or approaches towards zero when you move towards the wall. Okay, so this signifies the existence of a velocity gradient. And the third point is the gradient of the main velocity along a direction normal to the solid surface is much larger than the gradient of the velocity along the streamwise direction or the flow direction. Okay, so this is the first concept that you remember. So I hope till here it is clear, because these are very important and fundamental concepts, easy to understand but very important. Okay, next, what are the boundary layer equations? Okay, what are the governing equations for boundary layer flow? Governing equations for boundary layer flow. What are the governing equations? See, in mechanics, all the processes are governed by certain differential equations. So similarly, what are the governing equations or the differential equation which is relevant to boundary layer flow? Okay, so see, in this live sessions there is not much time allotted that we can derive all this governing equation, because it's a very elaborate procedure. If you follow any standard textbook on fluid mechanics, for example by Som, Vishwas and Chakravarti, or maybe fluid mechanics by Fox or Young, Monsoon and Okishi, you will find the detailed derivation, but I will simply write the direct form. Okay, the direct equations or the governing equations which are there. Okay, so what are those equations? The equations are in non-dimensional form, of course. The equations are for 2D case: u star del u star by del x star plus v star del u star by del y star minus of del p star by del x star plus 1 by re, where re is a Reynolds number, del 2 u star divided by del y star square. This is the first equation. Del p star by del y star is equal to 0, and del u star by del x star plus del v star by del y star is equal to 0. So these equations are known as these three equations are known as Prandtl's boundary layer equations, and they serve as the governing equation for a boundary layer, but definitely for a 2D case. Okay, and definitely for incompressible fluid. Okay, now what are the star variables? The star variables signifies non-dimensional form of the variables. So what are these? The non-dimensional form of the variables: u star is equal to actual u divided by the free stream velocity capital U. Say we have a flat plate like this. This is the boundary layer, and inside the boundary layer the velocity is u and v, something like this. Okay, but far away from the plate the free stream velocity is u infinity, or the velocity along the main flow direction outside this boundary layer is basically u infinity or capital U. Okay, so in different books you will find different conventions. Similarly, v star is v star is V divided by capital U. Then what is X star? X star is X by L, where capital L is the characteristic length scale of the problem. If you consider the boundary layer flow or the flow over a flat plate, then the total length of the plate can be taken as the characteristic length scale. Okay, so X star is X by L, Y star is Y by L, P star is non-dimensional pressure. It is P divided by rho capital U square. Okay, so basically the non-dimensional form of the equations are these. So these are the governing equations, but definitely if you want to find a unique solution to this governing equations, you need certain boundary conditions. Okay, so what are these boundary conditions, or what are the set of available boundary conditions? The set of available boundary conditions are, okay, at the solid surface. So at the solid surface, what will be the value of y star? The value of y star will be 0. So at the solid surface, u star equal to v star equal to 0. So this is from the no slip condition. Okay, or you can write something like this: y equal to 0. In dimensional form it is u equal to v equal to 0. Okay, then at y equal to delta. So what is delta? Basically, say this is our flat plate, the boundary layer thickness, okay, is denoted by delta. So this delta is basically a function of x, where x starts from the start of the plate. So this is the x direction. So at the edge of the boundary layer, okay, that is at y equal to delta, u, that is the flow u velocity, the u distribution or the attraction velocity is equal to the free stream velocity. Okay, u. So these are the boundary conditions that are available. Okay, so these are the basic concepts that you should know. Again, there are some, while solving the problems you will find some notations. So what are those notations? See, since there is a practice of depicting everything non-dimensionally, so there is a parameter eta, which is, eta is basically what? Eta is equal to y by delta. Okay, eta is equal to y by delta. So these things will get clear when we will move to actual flow problems. Okay, when we will be actually solving the problems. Okay, one more condition is, see, if you consider the flow over a flat plate, okay, if you consider the flow over a flat plate and say this is the boundary layer, then where do you think inside this boundary layer the shear stress tau is maximum? Okay, where do you think the shear stress tau is maximum? Shear stress tau will be maximum at the location where the velocity gradient del u by del y is maximum. Okay, so if you consider the velocity gradient, okay, say this is the velocity distribution. So where is the velocity gradient maximum? Velocity gradient is maximum at this point. It is the point of contact between the fluid, the point of contact in the fluid and the solid surface. So here the shear stress is maximum. So if we write this as tau 0 or tau s, maybe tau solid. So in different books you'll find, or some books use tau w, that is w signifies wall. So on the solid surface the shear stress is maximum. And what is the value of this tau s or tau w or tau 0? The maximum shear stress tau max is equal to mu del u by del y, but del u by del y at which location? At y equal to 0. Okay, then see, one important concept is of boundary layer thickness. The next important concept is of boundary layer thickness. Okay, it is the concept of boundary layer thickness. Now if you consider the flow past a flat plate and say this is the boundary layer, then we have seen that boundary layer thickness is denoted by delta. But how can you quantify or how can you obtain the value for this boundary layer thickness? So there are different approaches. Okay, so if you apply the conservation of momentum, you get a thickness which is known as displacement thickness. If you apply the principle of conservation of linear momentum, the boundary layer thickness that you obtain is known as momentum thickness. Okay, so what is displacement thickness? Let us see one by one. What are the definitions for displacement thickness? So displacement thickness usually denoted by delta star. Okay, it is the displacement thickness usually denoted by delta star is what? It is the distance by which the external potential flow is displaced. External potential flow is displaced outwards due to the decrease in velocity in the boundary layer. So this is the definition of boundary layer thickness. So please read this definition once. Try to uh, try to understand what these terms mean so that you can visualize what exactly is displacement thickness of a boundary layer. Okay, let me underline the important part. The first important term that you should understand is external potential flow is displaced outwards due to the decrease in velocity in the boundary layer. So these are the two important components of this definition: external potential flow, okay, and decrease in the velocity in the boundary layer. So first of all, let us see what is this, the external potential flow. So what is potential flow? What is potential flow? See, in one of the live sessions, maybe in live session number 2, live session for week 2, we have discussed the concept of potential function, velocity potential function phi. Okay, velocity potential function phi. Now, what was the definition of velocity potential function phi? Definition of velocity potential function phi was that we have discussed that it is a scalar function. Okay, it is a scalar function such that u, that is the x component of velocity, is given by delta phi by del x. The y component of velocity is given by the gradient of this function along y direction, and the z component of velocity given by the gradient along z direction. So if you keep our concentration or focus, just for simplicity, only in case only for two dimensional flow, then phi is a scalar function such that u is equal to del phi by del x and v is equal to del phi by del y. Okay, now this is the definition of phi. But if for a particular flow situation, we have discussed some properties of phi. If the value of phi exists, okay, then what can you infer about the type of flow? If the value of phi exists, then we can straightaway say that the flow is, any answer? If the value of phi exists, then we can straightaway say that the flow is irrotational. Okay, how for 2D case we have seen that omega z is equal to half of del v del x minus del u del y. Okay, now if we use the definition of phi, if phi exists, then what? V can be written as del phi by del y. So this becomes del 2 phi del x del y. And if you can be defined as del 2 phi del y del x. Now since these are continuous function of space x and y, so this term and this term are equal and it becomes 0. So simply the existence of phi confirms that it is irrotational flow, that is omega z is equal to 0. Okay. Now if the flow is irrotational, okay, if the flow is irrotational, it means that the velocity gradient, see, irrotational flow means what? If it is a three-dimensional flow, then this omega is basically a vector which has three components, omega x, e1 cap maybe, omega y, okay, or let us write like this, omega x I cap, omega y j cap, plus omega z k cap. Okay, now if the flow is irrotational, it means that omega is equal to 0, that is the omega x, omega y and omega z, the all these values are equal to 0. It means that there is no velocity gradient. Okay, there is no velocity gradient. So if I take any direction as s, then del u by del s is always equal to 0. Okay, there is, means sorry, the velocity, sorry, yeah. So basically what was our discussion, that if the flow is irrotational, then all these components are equal to 0, this component and this component, so irrotational flow. Okay, so if you restrict our discussion till this point, because this we have already discussed in maybe week 2's discussion, so now let us again come back to our original definition of displacement thickness. So the word was external potential flow. So what is potential flow? Potential flow is a flow for which potential function exists, phi exists, and if phi exists, then we say that the flow is irrotational. Okay, so what is an external potential flow? External potential flow is a flow for which the value of phi exists. And why it is known as external flow? Because see, there is a flat plate. For example, if you take flat plate and the flow is taking place externally over this flat plate, so that is the meaning of external potential flow. Okay, is displaced outwards due to the decrease in velocity in the boundary layer. Okay, so what is the second component of this definition? Okay, what is the second component of this definition? So if you look at the second component, for the second component, I will ask all of you to at least have a look on the chapter on boundary layer theory in the book by Young, Monsoon and Okishi, because there they have a very well elaborated pictorial representation of this different types of thickness. But I will try to in this limited time available, I'll try to explain the same concepts here also. Okay, now let us consider that there is a flat plate. Okay, and inside the boundary layer, how the velocity distribution will look like? The velocity distribution will look something like this. Okay, inside this boundary layer. Sorry. Sorry. Something like this. Okay. So inside the boundary layer, the velocity distribution will look something like this. Okay. Suppose if there was no solid boundary. Okay. If there was no solid boundary, say for example here, when there is no solid boundary, how the velocity distribution will be? Everywhere it will be, say here, see, at this location, at the edge of the boundary layer, what is the value of the velocity? It is capital U, or let me write U infinity. Okay. But if there was no solid boundary, then starting from y equal to 0 to y equal to delta at a distance, the velocity everywhere will be U infinity. Okay. So here the distribution is basically a rectangle. Okay. For this case, and here it is something like this. Okay. So definitely there is, see, what is mass flux? How can you express mass flux? Rho into U. Okay, rho is the density, and what is U? U is the velocity. Okay, so what is mass flux? Mass per unit area per unit time. Okay, so can be represented by rho into U. Okay, now, so if you multiply this mass flux, that is density into the velocity, with certain area for a particular time, or if you multiply it only area, what will you get? You will get mass per unit time. Okay, so let us say the dimension or the width or the dimension perpendicular to the plane of this screen is, say, 1. Okay, say the width, say I am writing width is equal to a, say a is equal to 1 unit, then it is something like this along this dimension. Okay, say we are measuring the flow from this side. Okay, then for this case, what will be the mass flux? Mass flux will be straightway rho into U infinity into 1. Okay, say this area is 1 unit area, 1 into, say, what is this length? This length is, say we are going from y equal to 0 to a length y equal to delta, so rho U infinity into 1 into delta. So basically you are getting rho U infinity into delta. But if the same mass flux you calculate for this distribution, okay, for this distribution, then do you think it will be the same value? No, because it is something like this. This is the rectangle. Okay, but for this entire portion the flow is not there. The flow, it is something like this. So this much portion is lost. Okay, this much portion is lost because of the formation of the boundary layer. Okay, so how do you compensate for this lost portion? So that is given by the distance by which the flow is displaced. Okay, so by how much amount you need to displace this flow, okay, so that this loss is overcome, okay, is given by the displacement thickness. So this is directly coming from the law of conservation of mass or the continuity equation. So this thickness is the displacement thickness. Okay, so by applying the law of conservation of mass, you can directly derive this expression, which comes out to be, sorry, which comes out to be the displacement thickness. I am not going into the detailed derivation because it has been already discussed in the main lectures. Okay, but I am just writing the expression. So it is from 0 to infinity 1 minus small u by u infinity into dy. Similarly, we have one more definition for boundary layer thickness, which is known as the momentum thickness. Okay, which is known as the momentum thickness, denoted by delta star star. Okay, so delta star star is the momentum thickness. Okay, delta star star is the momentum thickness. So what is momentum thickness? Okay, what is momentum thickness? So momentum thickness is basically, see, the displacement thickness was associated with the loss of mass, and momentum thickness is associated with the loss of momentum in the boundary layer as compared with that of potential flow. And similar concept means if you equate the momentum or if you apply the law of conservation of linear momentum, you will get that momentum thickness delta star star is equal to integration from 0 to infinity u by u infinity 1 minus u by u infinity dy. Okay, so this is the expression for momentum thickness. Okay, so these two expressions you can derive, even if you have not if you have followed the lectures you already know this, and if you have not, please follow the lectures so that you will have a better idea how you can apply this mathematically by applying the principles of conservation of mass or conservation of linear momentum, or you can follow any standard textbook on fluid mechanics. So these are some of the important concepts. Then the next important concept, at least for undergraduate level, which is very important, is momentum integral equation. Okay, it is the momentum integral equations for boundary layers. Momentum integral equations for boundary layers. Okay, so here also there is a detailed elaborate derivation involved, but I will directly write the equation for von Karman momentum integral equation when the pressure gradient is 0. Okay, so von Karman momentum integral equation for 0 pressure gradient is given by d dx of u infinity square del star star tau w by rho, where tau w is the shear stress on the wall. Okay, and if it is for a non-zero pressure gradient, just one single term will be added on the left hand side of this equation, which is delta star u infinity du infinity by dx. Okay, so these equations you can either derive it from uh, by using a free body diagram, or you can also use the Prandtl's boundary layer equations. Okay, and then you can integrate the equations within the two extreme limits of the boundary layer, that is from y equal to 0 to y equal to delta, and then you can get it mathematically also. Okay, then the last important concept before we move to the problems is the separation of boundary layers. Okay, I'm giving all of you 5 minutes to revisit the concepts that we have discussed today, so that we can smoothly move to this concept of separation of boundary layers and then jump to the problems for today's practice session. Any doubt? Okay. So in that case, you can move to the next concept, that is the separation of boundary layers. So what is separation of boundary layers? See, when say say this is a solid surface of arbitrary solid surface, flow is taking place. When the boundary layer separates from this or detached from this solid surface, it is known as separation of boundary layers. But you need to understand why this boundary layer separation takes place. Okay. In the separation of boundary layer, pressure gradient plays a very significant role. How? First of all, let us consider, see, part by part, let us consider. Okay. Let us consider the flow part by part. See, we say that the pressure gradient del P by del X along the flow direction X is favorable. We say that the pressure gradient is favorable when del P by del X is when this pressure gradient is less than 0. And we say that the pressure gradient is adverse when del P by del X is greater than 0. What is the meaning of this? The meaning is, suppose this is, let us consider again the case of the flow past a flat plate. Say the flow is taking place along this direction. Say the direction is X. Then favorable pressure gradient means what? Del P by del X is less than 0. So if you consider any 2 point 1 and 2, so point 1 and point 2, when P2 is less than P1, okay, when P2 is less than P1, we say that the pressure gradient is favorable. And when P2 is greater than P1, we say that the pressure gradient is adverse. Okay, so this is the first point. Okay. Second point, outside the boundary layer. Okay, outside the boundary layer, what happens outside the boundary layer? Outside the boundary layer, see what are the forces? There is no viscous force, there is pressure force, and there is inertial force or streamwise acceleration. Force due to streamwise acceleration. So here there are two cases. Case 1, when the pressure gradient is favorable. Okay. So when the pressure gradient is favorable, see, inertial force is always acting along the flow direction. It will try to assist the flow. Assist the flow. If the pressure gradient is favorable, means what? Say this is the flow direction. This is point 1, this is point 2. So for favorable pressure gradient, P2 is less than P1. So pressure force at 1, say PA I am writing. So pressure force at 1, say FP1 is greater than pressure force at point 2. So there is a net pressure force delta FP. Okay, see, if FP1 is greater than FP2, the net pressure force will be acting along the flow direction. So basically the inertial force as well as the pressure force, they are acting along the same direction, and they are uh, basically helping in the formation of the boundary layer. Okay, so there is no scene of boundary layer separation. But in outside the boundary layer is outside the boundary layer, let us consider this was the first case when the pressure gradient was favorable. But when the pressure gradient is adverse, then what happens? The inertial force acts along this direction. Okay, it supports the flow or the formation of boundary layer. Pressure force, the net pressure force acts in the opposite direction, but magnitude wise it is not that large. Okay, and normally see, since we are discussing the flow outside the boundary layer, there is no case of separation of boundary layer. Okay, so there are two possible cases. One is the pressure force is either along the streamwise along the streamwise flow direction, or the pressure force is opposite to the streamwise direction. But important discussion comes into picture when we do the same analysis inside the boundary layer, when we perform the same analysis inside the boundary layer. Now inside the boundary layer, when the pressure gradient is favorable. Okay, so no, before that, what are the forces that are acting? One is the force due to streamwise acceleration. Say I'm writing Fi, the inertial force. Okay, or rather than giving the direction, let us first of all list the forces. So one is the force, inertial force Fi, then we have the viscous force Fv, and then we have the pressure force Fp. Okay, now if case 1, okay, case 1 when pressure gradient is favorable, that is del p by del x is less than 0. When pressure gradient is favorable, then inertial force Fi will always act along the flow direction. We have seen that the pressure force Fp will also act along the x direction only. Viscous force will be always opposite to the flow direction, because it is the shear force or the shear stress, right? The shear force. But since inertial force and pressure forces, they in a combined manner opposes the viscous stress. See, this Fi and Fp helps in the growth of the boundary layer, and this Fb tries to detach the or separate the boundary layer from the solid surface. But Fi and Fp, they give a combined fight to the viscous stresses, and boundary layers remain attached. Okay, but if pressure gradient is adverse, that is if del p by del x is greater than 0, then what happens? That is case 2. Inertial forces Fi alone plays the role of keeping the boundary layer attached to the solid surface, and it is opposed by the viscous force as well as the pressure force, and as a result a point comes when the boundary layer separates. Okay, and that separation point is basically given by this equation. When del u by del y at y equal to 0 is equal to 0, we say that it is the point of separation. So at the point of separation, del u by del y, that is the velocity gradient, and the solid surface is equal to 0. Okay, so this is the physics. See, there are some books which have directly given you the condition del u by del y at y equal to 0 is equal to 0 at the point of separation, but you should understand the physics, the under background physics, what is happening. Okay, so this is the physics. Any doubt? Any doubt? Please take a break for 5 minutes, and after 5 minutes we'll start with the problem sessions. Okay, so this is the pictorial representation of boundary layer separation. So see, this is the point where the separation starts, and after that the flow is reversed. Okay, flow reversal takes place. So now let us move to the problem practice session. So this is the first problem. So it states that what is the state problem statement? Water flows. Okay, so the fluid is water. Water flows over a flat plate. So it is a flat plate at a free stream velocity of 0.15 meter per second. There is no pressure gradient, and the boundary layer is laminar whose thickness is 6 mm. You have to assume a sinusoidal velocity profile given by this u by u infinity sine pi by 2 y by delta. For these flow conditions, you have to calculate the local wall shear stress, that is tau w, and skin friction coefficient. Okay, skin friction coefficient on the plate. See, shear stress is because of friction. So on the surface of the plate, what is the skin friction coefficient? CF. Okay, that you need to calculate. Okay, the value of mu for water is 1.02 into 10 to the power minus 3 kg per meter second, and the density of water is 1000 kg per meter cube. So please try this problem for some time, and then we'll discuss the solution. And if you have obtained some answer, please tell me, or you can also mention in the chat box. Any answers? Okay, let us look at the solution. Okay, so tau is mu del u by del y. Now, if you try to write this in terms of u by u infinity, okay, means in non-dimensional form, okay, in non-dimensional form, or basically see u, the value of u is given to you, okay, so you should be able to get this equation. How? Let us see. Okay, so we know that tau is equal to mu, sorry, del u by del y. What is the value of u? The value of u is, see, it is given to you that u by u infinity is sine pi by 2 y by delta. Okay, sine pi by 2 y by delta. Yes. Now, from this, what will be the value of u? Value of u is u infinity into sine pi by 2 y by delta. So what will be del u by del y? Del u by del y, u infinity cos pi by 2 y by delta into what? Pi by 2 delta. Okay, so tau can be written as mu u infinity divided by, so mu infinity pi divided by 2 delta into cos pi by 2 y by delta. Okay, so this is the expression for tau. But if you want to find tau w that is at the wall, what is the value of y? Value of y is equal to 0. So it is basically cos 0. So cos 0 is 1. So tau w will be equal to mu u infinity pi by twice delta. Okay. So this is the thing that you are getting. If you see what is this 1.57 u mu u infinity delta. Okay, so mu u infinity delta, so pi by 2 basically. So 3.14 divided by 2 is approximately 1.57. That's it. Okay, and at y equal to 0, this is the value. So the value of tau wc here, you know the value of mu, it is given to you. You know the value of u infinity. Infinity is the free stream velocity, which is 0.15 meter per second. You know the value of delta, so 0.04 newton per meter square. And what is screen friction coefficient? CF. CF is tau w by half of rho u square. Okay, rho u means u infinity square. So the value is 3.5 into 10 to the power minus 3. Okay, so this is the answer. So it was a very simple problem. Any doubt? Is this problem clear? Very simple problem. This is the answer. Okay, this is the answer. Is it clear? Okay. So if there are no doubts, then we can move. Again, it is a very simple problem. So I'm sure that it is clear to everyone. Let us move to the next problem. Yeah, this problem is a very interesting problem. See, air at standard conditions. So the flowing fluid is air, flows over a flat plate. The free stream speed is 3 meter per second, that is u infinity. You have to find the displacement, you have to find the boundary layer thickness delta and the wall shear stress at x is equal to 1 meter from the leading edge. Assuming a cubic velocity profile. Okay, for air the value of kinematic viscosity is given to you and the density is given to you. So see, if you are considering the flow over a flat plate, okay, and if this is the flow direction, here from here, this is say x equal to 0 and this is x equal to L, where capital L is the total length of the plate. Then this x equal to 0 is known as the leading edge and this is known as the trailing edge. Okay, so at some distance where x is equal to 1, okay, you have to find the value of boundary layer thickness delta and you have to find the value of tau w at its location. Okay, this boundary layer is basically a function of x. Okay, that is the distance from the leading edge. So you need to find it. Okay, but again there is a twist here that you'll have to assume a cubic velocity profile. This is what makes the problem interesting. Okay, this is what makes the problem interesting. So how can you write a cubic profile? Okay, a general cubic profile can be written as, say, a x cube bx square cx plus d. So this is a general cubic profile. So for velocity, you need to adopt a cubic profile. Okay, you need to adopt a cubic profile. But if you adopt a cubic profile like this, these x terms will be the velocity terms. Means not the velocity terms, basically y by delta. As you said it is normally written as y by delta is eta. So these will be eta terms. But the challenge is in calculating the values of these coefficients. Okay, the challenge lies in calculating the values of this coefficient. So that is the challenge. So since it is a bit new type of problem, I'll not ask you guys to solve this problem or try this problem at the very beginning. We will discuss the solution. Okay, we'll discuss the solution step by step. But I hope the problem is clear. So if there is any doubt till this point, if the problem is any doubt, anyone who has any doubt, or can we move to the solution? Okay. So if there is no doubt, then I think we can move to the solution part. Yeah. So as it is given to you that you need to adopt a cubic velocity profile. So u by u infinity is the velocity profile a0 plus a1 eta plus a2 eta square plus a3 eta cube, where eta is equal to y by delta. Okay. Now as I mentioned, the challenge is to determine the values of these coefficients a0, a1, a2 and a3. So basically there are how many unknowns? There are 4 unknowns. So in order to obtain the values of these coefficients or of these 4 unknowns, you need 4 equations. Okay, that is the challenge. So what you can do is, now you can apply the boundary conditions. But you cannot apply any boundary conditions. Okay, you need to apply boundary conditions which will satisfy the boundary layer flow situation. Okay, so the first boundary condition at y equal to 0 and that u equal to 0, at y equal to 0, u equal to 0, value of eta will be what? See, this is the first condition. At y equal to 0, u is equal to 0. So at y equal to 0 means what? Eta is equal to 0 because eta is equal to y by delta. Eta is what? Eta is y by delta. So if y equal to 0, it means that eta is equal to 0. And at y equal to 0, u is equal to 0. So u by infinity equal to 0. So this is the first condition. At y equal to c, this is the second condition. Okay, we'll come to this condition later. At y equal to delta, that is at the outer edge of the boundary layer, u is equal to infinity. So when y is equal to delta, the value of eta is 1 because y by delta, and u by infinity will be 1. This is the second condition. So these two we have already seen. These are the boundary conditions for the Prandtl's boundary layer equation. Yeah. Then at y equal to delta, del u by del y equal to 0. Why? You consider the flow, you consider the flow past a flat plate. You consider the flow past a flat plate. Okay. This is the boundary layer. Okay. Now, above this, outside the boundary layer, what is the value of u? U is equal to e infinity. Okay. And at y equal to delta, at this point, what is the value of u? U is equal to u infinity. So after this, along y direction, del u by del y, see the value of u is e infinity everywhere, from starting from the edge of this boundary layer, outer edge of this boundary layer, till infinity. Okay, or till the extent of this flow, the value of u is equal to infinity everywhere. So what will be del u by del y? Del u by del y, see, if there is no change in u, the value of del u by del y is 0. So that is the third condition. At y equal to delta, del u del y equal to 0. So at y equal to delta, the value of eta is 1 and del u by del y is equal to 0. So you need to write this in terms of eta. So what you can do? See, del u by del y. Okay. Now eta is equal to y by delta. So y can be written as eta into delta. See, if what I can do is, I can multiply 1 u infinity, then I have to divide it by infinity, del u by del y. What I will get? I will get 1 by u infinity. Sorry, u infinity. Okay, del u by u infinity, del y can be written as eta into delta, but delta is a constant, so I will get u infinity by delta into del u by u infinity divided by del eta. But at y equal to delta, the value of this is equal to 0, but u infinity by delta is something which is finite value. It may be zero value, but practically if you think, it is a finite value parameter. So the only possible way is that del u by, if del u by del y equal to 0, in terms of eta it will be del, okay, it will be what, it will be del u by u infinity divided by del eta is equal to 0. This is the only thing. Okay, now let us come to the second part. At y equal to 0, at y equal to 0, that is on the surface of the solid. Okay, at y equal to 0, here at y equal to 0, we know that u is equal to 0, but del u by del y is maximum. Okay, at y equal to 0, u is equal to 0, but del u by del y is maximum, because the velocity gradient is maximum here, right, from the no slip condition. Now if you consider this is a separate function, say f is equal to 0, so if f is maximum at a point, then at that point the value of del f by del x will be what, 0, is not it? The value of del f by del x will be 0. So f is what, sorry, yeah, see, let us not discuss like this. Suppose there is a function f. Okay, now at the point of maxima, f dash will be equal to 0, maxima or minima, but if it is a maxima, f dash will be 0. Fine. In our case, we know that del u by del y is maximum at y equal to 0. So it means that del y of del u by del y will be 0 at y equal to 0. So this gives us this condition, the last condition, that at y equal to 0, del 2 del y square equal to 0. And similarly, in a similar manner, see how we can arrive at this condition. We'll see at y equal to 0, value of eta equal to 0, and this condition becomes this. How, we will see. So our condition is basically what, it is del 2u del y square. Okay, so del 2, see, u infinity by u infinity del y, instead of y you can write eta into delta square. Okay, u, so u infinity by delta square. Okay, del 2 u by u infinity divided by del eta square. Okay, so if this is equal to 0, if this is equal to 0, then it means that this term is equal to 0. Okay, okay, 0. So see, now we have 4 unknowns, a0, a1, a2, a3, but we have 4 equations also. Okay, or 4 boundary conditions. So if you apply these boundary conditions, you will be basically getting system of linear equations. See, for example, a0 equal to 0, a2 equal to 0, a1 plus 3a3 equal to 0, a1 plus a3 equal to 1. So if we use all this condition, you will be getting that value of a0 is 0, a2 is 0, a1 is 3 by 2, a3 is minus half. So finally, the cubic velocity profile for a boundary layer case is this: u by infinity 3 by 2 eta minus half of eta cube. Okay, so this is that is the reason why I have put this problem in the practice session, because it clears a lot of concepts at the same time related to the concept of boundary layer flow. So is it clear till this point? Any doubt? Please go through the discussion once again, okay, for this particular problem, and please ask me any doubt related to this problem or whatever we have done till now. Okay, we have not solved the entire problem, but the most critical part of the problem we have completed discussing the most critical part of the problem. So go through it once again and then tell me. Okay, so is everything clear? Okay, so there is no question, then I can assume that everything is clear. So now see, so now we have determined the cubic velocity profile that is suitable for this problem. So what is that profile? The profile is 3 by 2 eta minus half of eta cube, where eta is equal to y by delta. Now you have to find the delta and tau w at x equal to 1 from the leading edge. Okay, okay. So we'll make use of von Karman momentum integral equation. Now since the flow is taking place over a flat plate, okay, since the flow is taking place over a flat plate, we can consider that the pressure gradient is equal to 0, or the pressure is constant over the entire plate. Okay, since there is no curvature, the same plane, all the points lie. Okay, so in that case, what will be the von Karman momentum integral equation? The von Karman momentum integral equation, this part will disappear, and we will be left with only tau w by rho equal to d dx of u infinity square delta star star. So see, in this equation, tau w is something that you need to calculate. The value of the density is given to you. Okay, u infinity square is given to you, which is a constant, but you need delta star star, that is the momentum thickness. So how you can calculate momentum thickness? Momentum thickness is integration from 0 to infinity, but practically it is basically the integration from 0 to delta, that is till the extent of the boundary layer. U by u infinity, that is the distribution, minus 1 by u infinity dy. Okay, but we have our u by u infinity in terms of what? Eta. So eta will be equal to, sorry, eta is what? Eta is equal to y by delta. Fine. Or y is equal to eta into delta. So what will be dy by d eta delta? So dy will be equal to delta into d eta. So instead of dy, we can directly write delta into d eta. Okay, when y is equal to 0, eta is equal to 0. So the limits of integration will be when y equal to 0, eta equal to 0. When y equal to delta, eta will be equal to 1. Integration 0 to 1, u by infinity, we are already having in terms of eta, minus 1 by u by infinity, which is already in terms of eta. Instead of d1, you can write delta into d eta. Okay. So now, see, this is the calculation. Delta integration 0 to 1, this is u by infinity, this is 1 minus u by infinity, delta into d eta, since delta is a constant, it is came out, and finally you are getting 39 delta by 280. Okay, so once you have delta star star, okay, once you have delta star star, tau w rho u square, see, this is what we have seen, no? Delta star star, delta star star is in terms of what? What is the value of delta star star that has been obtained? Delta star star is, sorry, 39 delta by 280. So this is what? 39 delta divided by 280 delta star star. So tau w by rho is equal to u infinity square will come out, then delta star star, there 39 will come out, 280 will come out, will be only left with d delta by dx. Okay, but what is tau w? Tau w is mu del u by del y at y equal to 0. So that also you can find. Okay, so you have all the necessary information. So tau w is 3 mu e infinity by twice delta. At y equal to 0, you can find it like this, or you can convert it in terms of eta, whatever is convenient for you. But if you do that, then instead of y equal to 0, you have to use the condition eta equal to 0, because at y equal to 0 is same as eta equal to 0. So now you have the momentum integral equation like this. From here you integrate and find the value of delta. But again there is a constant of integration. So at constant of integration, see, if you look physically, this is our flat plate, this is the leading edge. At the leading edge, what is the value of delta? That is, what is the value of delta at x is equal to 0? The value of delta is 0. Use that condition, you will be getting the value of this C1. Then you find the value of delta. Once you have the value of delta, you can see that it is in terms of x and Rex. What is Rex? Rex is u infinity x by nu. Okay, the Reynolds number that governs the flow in boundary layer is basically in terms of the characteristic length is the distance from the leading edge of the plate. So Rex. So after that you can find everything is given to you. You can find tau w. So see, in short, what is the procedure? The procedure is, since a particular, in the question it is given to you that you have to make use a particular velocity profile, you have no idea, the exact profile is not given to you, so you assume the most general form of that profile. For example, in this case it was given to you that it is a cubic profile, so you write the most general form of that cubic profile, and based on the number of unknowns you try to construct boundary conditions, but which are feasible to the flow characteristics inside the boundary layer. If you use any boundary condition, then it will give you, definitely it will give you some value for the coefficient. Okay, but finally the profile that you will obtain will not be representative of the actual boundary layer flow case that you want to solve. Okay, So you must be very much careful in selecting or in constructing the boundary conditions for obtaining the value of this unknown coefficients. Okay, you must be very much careful while you are doing this. Now once you have the values for this unknown coefficient, next what you do, next you find tau w from Newton's law of viscosity, but at y equal to 0. Then you find the momentum thickness. Okay, then you check which form of von Karman momentum integration equation you need to use, whether it is the one where whether in the problem pressure gradient exists or it is without pressure gradient. So depending on that you decide, and once you have decided all these things, you simply need to put the parameters and the values that are given to you in the equation and you get the answer. Okay, so that is the case. Now this problem, once you have understood this problem, I am giving you the next problem. You have to solve it by yourself. Means we will discuss the solution, but the procedure is same as that of the problem we have solved just now. In fact, it is a simpler version. So again the same fluid, air. Okay, it is air which moves over a flat plate with a uniform free stream velocity, that is u infinity, of 10 meter per second at a position 15 centimeter away from the front edge of the plate, that is the leading edge. What is the boundary layer thickness? That is, you have to find delta at x is equal to 15 centimeter or 0.15 meter. Okay, you have to use a parabolic profile. Yeah, this is important. Parabolic profile in the boundary layer. The value of nu and rho for air are given to you. So here u by u infinity a0 plus a, sorry, a0 plus a1 eta plus a2 eta square. Okay, parabolic profile. Now you need how many equations? You need three equations. So please construct the velocity profile and then solve the problem. I am giving you around 10-15 minutes of time to solve this problem. Whatever values you are obtaining, first of all you please report the value of the expression for the velocity profile and then you solve the problem. Okay. Okay, any answers till now? So just like the previous problem, u by infinity a plus by plus cy square. Okay, you can use this, or you can use in terms of eta also, that is your wish. Okay, but what are the conditions? At y equal to 0, u equal to 0, at y equal to delta, u equal to infinity, and at y equal to delta, del u by del y equal to 0. Okay, so these three conditions we have already seen. So you simply use that, and then you evaluate the constants. Okay, you evaluate the constants. So three unknowns, three equations. So you'll be getting a system of linear algebraic equation. Solve it, and the velocity profile is twice eta minus eta square. Then you obtain the value of tau w, that is mu del u del y at y equal to 0. Okay. Then you apply momentum integral equation again. Since this is a flat plate, it is a flow with zero pressure gradient. So if since this is a flow with zero pressure gradient, you simply find the momentum. See, this is the momentum thickness, and then based on this, see, here you have obtained the value for delta square by 2 is this. After integration, definitely some c. How will you find c? X at delta at x equal to 0 is 0, so c is equal to 0. So you find delta by x something like this. Okay, then at x equal to how much? 15 centimeter or 0.15 meter, what is the value of delta? So this is the problem. Okay, so this is similar to the previous problem, only the profile is different. So please practice some more problem like this. And then the last problem. A smooth flat plate 1.5 meter wide and 20 meter long is subjected to flow of water along its length with a velocity of 2 meter per second. Find the extent of the laminar boundary layer on the plate. See, whenever boundary layer formation occurs, till a certain length, it will be laminar, then there will be transition, and then it will be turbulent. Okay. So you have to find the length, extent of the laminar boundary layer, the length till which the boundary layer remains laminar. The thickness of the boundary layer at the edge of the laminar boundary layer and at the trailing edge. So thickness of the boundary layer, okay, at this location and finally at this location at the end, and then the shear stress at the trailing edge. Okay, value of rho and nu are given to you. So Reynolds number UL by nu. See, the length of the plate is given to you, which is 20 meter. So what is the Reynolds number? 4 into 10 to the power 7. Therefore the boundary layer is turbulent at the trailing edge. So this is the Reynolds number at this end. So at the trailing edge it is turbulent. Now see, critical Reynolds number, that is the Reynolds number till which the boundary layer remains laminar is 5 into 10 to the power 5. So this is a fact that you need to remember. Okay. So from this condition you can find the value of x critical, which is 25 centimeter. Okay. So the laminar boundary layer exists in the first 25 centimeter of the plate. This is the first part. Second part, what is the thickness of the boundary layer at this location? So thickness of the boundary layer at this location, you can directly use the formula. Okay. At the trailing edge, as the Reynolds number is greater than 10 to the power 7, the thickness of the boundary layer is obtained by putting x equal to 20 meter in the equation C. For turbulent boundary layer, you have to make use of the turbulent boundary layer equation. Okay. This one, and you find the thickness of the turbulent boundary layer. And then the shear stress coefficient in the turbulent boundary layer, the skin friction coefficient. You see, these are the formula that you need to remember. There are lots of formula given by different researchers. So it is better if you make a table, means in your notebook you make a table and you write this all this formula. Okay, formula for delta, corresponding formula for CF, corresponding formula for maybe this thing. Yeah, CF is there, delta is there, delta L, delta T, all this thing, and you practice the problem. Okay, that is the only way. You practice more and more problems, that will give you lots of confidence. So with this, let us end today's session. If you have any doubt, you can ask. And if not, then you can stop this meeting. Okay, it seems that there is no doubt. So we can stop here. Again, meet next week, the same time. Thank you.